Hello, my name is Griggs. I'm a sophomore chemistry major here at UNC. I would like to be a chemistry mentor because I did it this fall and I had a wonderful time doing it, especially heading up a recitation every week. It was a great experience to interact with new students and really just help them on their chemistry journey here at UNC.
Here we have a problem from the first unit of Chemistry 241, focused on acid-base chemistry. So the statement is, calculate the equilibrium constant for the following reaction. Now, first thing we might notice is that this bicarbonate ion is acting as a weak base, and it's being added with OH ions. Now, immediately we might recognize this as a titration as we see its conjugate base on the other side with water. Now, we've calculated a lot of equilibrium constants in Chemistry 102, even a little more in 241, but this looks a little weird. At first glance, this seems a little odd. However, one thing that we might need to recognize and one thing that we might need to remember from Chemistry 102 is that the reverse of the reaction is equal to the inverse equilibrium constant for the forward reaction. Now, CO3 2- with H2O going to OH ions and this bicarbonate ion seems a little more familiar. So if we write this out, now, this looks just like a weak base dissociating. That's exactly what it is. And that is where we're going to get our equilibrium constant for this titration. So, we know that since we are looking for this equilibrium constant, we can say that is equal to the inverse of this equilibrium constant, which is going to be 1 over Kb. But we do need to be careful, especially using our table from the test. We are giving Ka values, and carbonic acid is a diprotic acid, dissociating twice, giving it 2 Ka values and 2 Ka values. So this carbonate ion is going to accept 2 protons. So we're going to make sure that we need this Kb1 instead of its Kb2. This Kb1 comes from Kw divided by the acid dissociation constant of bicarbonate. And now we realize we are looking for its inverse. We can just simply take Ka2 divided by 10 to the negative 14, and we will get 4.7 times 10 to the third.